All right, so far we've gone over two uses of group theory, right? Group theory is basically this business of using point groups in chemistry we're talking about, although there is a group theory associated with mathematics, just pure mathematics as well. Um, we've gone over two uses of group theory, which are chirality, determining if a molecule is in a chiral point group or not, and whether or not there's a dipole moment. These two examples, these two uses are very straightforward to use. You just need to figure out what the point group is, right? And then you kind of have all the information that you need. They're kind of limited, of course. There's a lot more to chemistry than these two concepts. And so one huge field of chemistry, right, is spectroscopy, using light to probe matter. Incredibly important experimental technique, right, which ranges from NMR spectroscopy to infrared spectroscopy to uh, X-ray spectroscopy to ultraviolet visible UV vis spectroscopy. So widely used techniques that give a wide range of information. Group theory really plays a central role, not only in coming up with the selection rules for these spectroscopies, a lot of these spectroscopies, but in allowing you to interpret spectrum, for example. Um, and then also group theory can be used for molecular orbital theory. Um, and so, in chapter 2, when we talked about the uh, different MO diagrams for um, homonuclear diatomics and heteronuclear diatomics, I kind of glossed over the symmetries of those orbitals, but now we'll be building up the language and the knowledge to be able to, eventually go back to some of those concepts um, and see how that can be really powerful for understanding molecular orbital theory as well, which is the leading theory based on quantum mechanics that describes all of chemistry's reactivity and the physical properties of chemicals. So extremely powerful. But these third and fourth applications take a little bit more groundwork for us to lay before we can dive into them. So that's what we're going to start to do in this video. And so the first skill we have to go over is a mathematical skill. Possibly familiar with this. This is matrix multiplication. So a matrix is just a set of numbers, okay, put in these brackets. And so this allows you to do math very easily and conveniently in multiple dimensions. And because there's so many different symmetry elements for different molecules, kind of each class of symmetry operators you can think of as a different dimension. And this is where this is all leading to. But a common operation that we'll be doing is multiplying matrices. And so the way to remember this is row by column, RC. And so if you multiply, for example, here shown two 3 by 3 matrices, the answer is the dot product. And it's done in this row by column way. So you're going to do the first, the first entry here of your resultant matrix at the position kind of 1, 1, the first position, it's going to be the first row dotted with the first column. So what does dotted mean? Dot product. So it means A11, whatever that value is, times B11 plus A12 times B21 plus A13 times B31. And so that gets you your first entry. So that expression that I just said out loud is right here. And that would be right here. And then you continue carrying on in this way. So if you wanted to do this entry next, you can see the expression here. You're going to go row by column. So again, you go the row, okay, and you dot it now with B12, B22, and B32. So it's shown here. And then this entry would be the next one. So you keep going and proceeding in that fashion. When you get to the second row, then you're going to be the second row dotted with the first column. That would get you this entry right here. So here's an example with some numbers and some smaller 2 by 2 matrices. So these two matrices, in order to do the evaluate the first parameter, we go 1, 0, dotted with 4, 2. So it's row by column. So that's 1 times 4 plus 0 times 2 is 4. Then we go to get this entry, we're going to go the first row dotted with the second column. So it's going to be 1, 0 dotted with 1, 3, gives you 1. And then 1, 2 dotted with 4, 2 gets you 8. And 1, 2 dotted with 1, 3 gets you 7. So the reason why we're doing this is, let me just stop right there, actually.